You know how sometimes you notice two things that seem to move together, and you can't help but wonder, hey, does one of those cause the other? Well, in the world of data, figuring that out is, well, it's everything. It's how we separate a random coincidence from actual solid proof. All right, let's get into it. So here's our game plan. First, we're going to talk about just spotting a pattern. Then we'll grab our basic tools for the job, covariance and correlation. After that, we'll figure out which specific tool to use, Pearson's or Spearman's. Then comes the big one. We'll tackle the infamous correlation versus causation trap. And finally, we'll lay out the actual roadmap for how you can prove one thing really does cause another.
Okay, so let's start at the very beginning. It all starts with an observation, right? You see two things that seem to be moving in perfect sync, and you have to ask, why? This is a total classic. You look at the data, and it's clear. When people buy more ice cream, the number of drownings also goes up. It's a real pattern. But does eating a pint of Rocky Road make you a bad swimmer? Obviously not, right? So what is going on here? How do we look at a pattern like this and not jump to a completely wrong and frankly ridiculous conclusion? Well, that's exactly what we're here to figure out. To start untangling that puzzle, we need to open up our statistical toolkit. And our first two tools are designed to measure exactly how two things change together. Let's meet covariance and its much more famous and useful cousin, correlation. So covariance is our first step. It's pretty basic. It just tells you the direction of a relationship. If it's a positive number, it means as one thing goes up, the other tends to go up too. If it's negative, they move in opposite directions. But, and this is a big but, the number itself is kind of useless for judging strength. It's unbounded, meaning it could be 15 or it could be 15,000. And without a consistent scale, you can't really tell if that relationship is strong or weak. And that is exactly where correlation swoops in to save the day. It fixes the big problem with covariance by standardizing the whole thing. It takes that wild, unbounded number and squishes it into a perfect, tidy little range, from -1 to +1. Now, all of a sudden, we have a clear map. +1 is a perfect positive relationship, -1 is a perfect -1, and 0 means no straight line relationship at all. Boom, direction and strength, all in one easy-to-read number. This table just lays it all out, nice and clean. Look at that range difference. Covariance is all over the map, while correlation is neatly locked between -1 and +1. But the other game changer is the units. Covariance is stuck with the units of your data, which gets messy fast. Correlation, it's unit-free. And that is huge. It means you can compare the relationship between ice cream sales and temperature to the relationship between hours spent studying and exam scores on the exact same scale. That's why correlation is the gold standard. All right, so we have established that correlation is the way to go. But it's not quite that simple. Turns out there's more than one way to cook an egg, and there's more than one way to calculate a correlation. So let's meet the two heavyweights, Pearson's R and Spearman's Rho. So the biggest difference between these two really just comes down to the shape of the relationship they're looking for. Pearson is a specialist. It is only looking for a straight line pattern, a linear relationship. Spearman, on the other hand, is way more flexible. It's looking for something called a monotonic relationship. And all that means is that as one variable goes up, the other one consistently goes up or down. It just doesn't have to be in a perfect straight line. Think of Pearson's R as the straight line detective. It's the most common type you'll run into, and its one and only job is to see how neatly your data points hug a single straight line. It's basically asking, how good of a fit is a straight line for this data? Spearman's Rho asks so much more relaxed question. It just asks, hey, when one variable increases, does the other one consistently move in the same direction? The speed doesn't matter. You could line up students by their height, then by their shoe size. The order will probably be pretty similar, right? That's what Spearman cares about, the rank, the order. This makes it amazing for relationships that have a curve to them, or for data that has some weird outliers, because it's not looking at the exact values, just their order. Okay, check this out. This is a picture-perfect linear relationship. You can just see it. As you move to the right on the bottom axis, you move up on the side axis at a really steady, predictable rate. This is textbook. Pearson's R would be super high here, probably something like 0.9 or higher, almost a perfect one. And this is where Spearman gets to show off. Look at that curve. As x gets bigger, y always gets bigger. There's no exception. It's a perfectly predictable relationship. Because of that, Spearman's Rho would be a perfect 1. But since it's not a straight line, Pearson's R would be something less than 1. It would see a strong relationship, for sure, but it wouldn't capture the true perfection of this nonlinear connection. So, we've got our tools. We know how to pick the right one. We can measure the strength and direction of a relationship like a pro, but now we've arrived at what is, without a doubt, the single most important lesson in all of statistics. Say it out loud with me, wherever you are. Correlation does not imply causation. One more time. Correlation does not imply causation. Just because two things are connected, even perfectly connected, it does not mean one is causing the other. This is the golden rule, and forgetting it is how so much misinformation gets started.
So why is this true? Well, there are a few big reasons. Maybe you have it backwards, reverse causation. Or, like our ice cream and drowning example, there's a sneaky third factor, a confounding variable. In that case, hot weather, that's causing both. It could even be a two-way street, where A causes B and B causes A. Or, and this happens more than you'd think, it could just be pure dumb luck. A total coincidence.
I love this quote because it just shows how silly it can be to assume causation from correlation. Yeah, you could probably find a strong negative correlation between the number of dinosaurs who could read and the dinosaur extinction event. But it would be completely and utterly meaningless, right? A pattern is just a pattern. The real work is proving why it exists. So that, of course, leads us to the big question. If a super strong correlation isn't enough to prove anything, what is? How do we climb the mountain from spotting a correlation to actually proving causation? Now, first things first, let's be super clear. Even though correlation on its own doesn't prove causation, causation absolutely requires correlation. I mean, think about it. If A causes B, they have to be related somehow, right? So finding a correlation is your ticket to the game. It's the essential first step. It doesn't mean you've won, but it means you're allowed to play. And this is how you play the game. To really establish causation, you've got to clear these 4 hurdles. First, you need that correlation we just talked about. Check. Second, the cause has to come before the effect, in time. Makes sense, right? Third, there has to be a believable explanation, a plausible mechanism for how one could cause the other. And finally, this is the really hard one, you have to do your best to rule out all the other possible explanations, all those sneaky, confounding variables. So there you have it, the complete toolkit, from spotting a simple pattern all the way to proving a cause. So now I've got a question for you. As you go through your week, listen to the news, scroll online, what's a common belief you hear all the time that's really just a correlation pretending to be a cause? Once you start looking for them, you'll see them everywhere.